Alright, we are talking about chapter 11, which is on correlation. So in this chapter as well as the next, we're trying to investigate whether there is a relationship or a link between two factors. Like, for example, the hours that you slept the night before and your mood. Is there some relationship between them that we call the correlation? Is there some correlation between them? That the number of hours slept affect your mood, or mood affect the number of hours slept, or some link between them? That is what we're trying to investigate. Now, if we have a sample of 6 people here, 6 people with hours slept and mood associated, according to some rating, I could graph them by way of a scatter plot with, for example, the hours slept on the horizontal axis and the mood rating on the vertical axis. And I could find some pattern in what the dots suggest. That there seems to be some line that resembles the relationship between these two variables. Something like that, maybe. And if a line is sloped like this, bottom left to top right, it means that if I increase the hours slept, then I expect my mood to be better. Increased hours sleeping should correspond to a higher mood rating. We're trying to see if visually, at least, by way of looking at a sample, there is a relationship that's suggested by the sample. So if the first step is to make a scatter diagram, I make the horizontal axis and the vertical axis, decide which one goes where, or the question will specify, then see the range of values that I have, and mark them off, and then, put a dot for each of the values that we have, and then we want to visually see, what does this suggest? Hopefully I have a large enough sample so that I can see a nice link between the two, but that's not always the case. If we look at loneliness versus depression as an example, I have 6 people again, and ideally we want a larger sample here. But because we want to do these things by hand, we have a limited number here to make it manageable. But in practice, we'll have much larger samples to work with. Let's just see where I am right now. Okay. So again, I have my, for example, loneliness scale here at the bottom and depression on the vertical axis, and I plot 1. Loneliness corresponds to depression of 2, so I put a dot there. 4, loneliness corresponds to depression level of 3, dot there, and I continue like that, and I have my sample sort of graphically represented in terms of loneliness and depression. And now when I look at that, do I see any pattern, any link between these two? Well, the sample is so small that it's really hard to see. But in general, I would have more samples to see if there is a clear pattern. So let me just go back here, loneliness versus depression. So I could say that, sure, I could see visually, maybe they suggest a line like that, and if I had more samples, maybe I would have more confidence in saying that. But that's only going to get me so far. I want a numerical measure to say there is a strong correlation, or there's a weak correlation, or no correlation, and which direction is the correlation? Does it slope up like this, meaning increased loneliness, higher depression, or maybe the other direction? I want to associate a number with it, so that I don't rely on my instincts for what it looks like. I can look at the number, calculate it based on what my sample suggests, and make a decision accordingly. Alright, so just to recap, I have two examples here. I have the loneliness versus depression example, where we're trying to see if there's a relationship between the loneliness of a person, the rating, and the depression. And with a sample of 6 numbers here, visually I see, yeah, there might be some positive correlation, but I want a number. I want my correlation coefficient to tell me exactly how strong is the correlation between these two. And is it actually positive, like visually it seems to be. The other example that we'll focus on is the love-conflict example, where the question is there a relationship between the love felt towards one's partner and the amount of conflict with that partner? So, in a sample of 7 people, we rate the love and we rate the conflict, and we get this scatter diagram. Now, because I don't have a very big sample, I can't say for sure. It might suggest some sort of negative correlation, that a lower love rating corresponds to a higher conflict rating. But again, I want my correlation coefficient, the measure to be the measure of how strong the correlation is, and is it a positive or a negative correlation. Now, to do that, we're going to go back to our loneliness and depression example and see the numbers that we have to work with. I have these ratings here and here, but I don't necessarily know if the size of the number means anything. I want a way to standardize it. I don't want the size of the number to really affect my correlation, because what if I look at another rating scale and the numbers are in the hundreds? That doesn't mean it's a stronger correlation just because the numbers are bigger. I want to standardize the numbers by way of my z-scores and then compare them and see if there's a correlation. So in order to do that, I need to look at the deviations from the mean. I need the sum of the squares in order to get the standard deviation. And then I remember that the z-score is calculated by way of my mean and standard deviation. For each score, I would get the z value. Standardizing it, so the size of the number isn't the factor, it's more the distance away from the mean in terms of standard deviation steps, like we've seen in the past. I'll do the same for the y values. I'll get z-scores for them as well. And now I want to see how these guys relate, and I'm going to do that by way of multiplying the two z-scores. Let's just see, and we'll come back to this in a second, let's just see the different things that could happen when I multiply the z-scores with each other. If they are both positive, then the product will be positive. To an x value far to the right, a y value far up is going to contribute a strong positive number to the correlation. A low number will indicate a negative z-score and a negative z-score for both, and multiplying them will still indicate a positive correlation. Low, low, high, high. If it's the other situation, a negative correlation, let's visualize it by way of something like this. So that was low, low, high, high. This one, a high x value corresponds to a low y value, and a low x value corresponds to a high y value for a negative correlation. Then it fits with what I want, because if one is high and one is low, they have alternating signs in the z-scores, and when I multiply them together, I will get a negative product as well. And then I have other combinations here. If one is sort of in the middle and the other one is positive or negative, anything in the middle is not really going to give me much of an effect. It's more as I go away from the means. So that does seem to help me find what I'm looking for in terms of measuring the correlation, positive or negative. So I'm going to multiply the z-scores together. We call those the cross products. We're multiplying them across. And we'll add them together to get the sum of the z-score. Now we haven't talked about this guy yet, just focus on the sum of the z-score. So I get a 4.39. And I know that if I have a strong correlation, this number will be bigger. Stronger correlations, two highs or two lows, those numbers will make bigger cross products here and give me a bigger sum. If I look at the love conflict example, and I do the same thing, I get my x values and my y values, calculate the z-scores for each. Each one has its own mean, its own standard deviation, own z-scores, calculate that in the same way, but with different standard deviations. Cross products, add them together, and now I get a negative 4.48. So these two examples seem to have the same strength in correlation, but one's positive and one's negative. All right. So I want it's going to turn out that a stronger correlation is going to have a greater product. But if I look at a couple of examples, if I take a couple of x and y values, I get a cross product of, let's say, 2.8. If I get more, of course, my cross products, my products here might add up because I have more of them to add up, and I might get bigger and bigger values. Does that necessarily indicate that I get stronger and stronger correlations suddenly? Not really. The numbers just get bigger and bigger because I keep adding them. And especially with a positive correlation, I will be adding more and more positive numbers here so that this number is going to grow and grow and grow the bigger my sample is. And that's not quite what we want, because it's the same correlation throughout. I just get more accurate when I look at larger samples. So, same thing here. If I just have a couple or a few of them versus the same relationship, but the variables are a little further apart, I get a cross product sum that's bigger, but it's the same relationship. So what I'm going to do to fix that is simply average out those cross products, or the sum of the cross product, and dividing that by n, the number of XY pair values that I have will do that, and that's what I'll call the correlation coefficient. So I don't want it to blow up just because I take more samples, more sample values, so I'm going to average them out instead. So look at the average cross product in a way, and that will be my correlation coefficient, little r. So I change everything to a z-score, calculate the cross product, add them up and divide by how many people there are in the study. If I look at my sleep mood example, I'll zoom in a little bit because it gets a little small. Maybe out one more. There you go. I have my x values, deviation squared, because I need the standard deviation to normalize, to standardize them by way of the z-score. Same for the y's, and I standardize them, multiply them together, add them up, and divide to get the average cross product. let's zoom out and go and check. Oops, that's the wrong direction. Scroll like this. Up to my two examples. Where is the first one? Not love conflict. Loneliness, depression. Loneliness, depression example. I have my x values. I have my y values. I need to calculate the deviations and the square deviation. Sum of the squares gives me the variance. Take the square root of that to get the standard deviations so that I can then divide each of these deviations by this to get the standardized z-scores in both cases. Then multiply the z-scores together, average them out, and I'll get a 0.73. Then I'm going to go down to the love conflict example, see what we get there. Same procedure, even though with just 7 points, it's a lot of work here, so we don't want this to get too big, even though bigger samples will indicate more representative information. Average out the cross products and I get a negative 0.64. So a positive and a negative, positive correlation, negative correlation, positive correlation, negative correlation. And then the size of this R is going to tell me the strength of the correlation. All right, let me make sure I'm saying everything I want to say. That is 11.4b. I want to say that. Okay, so really sort of the last thing that we want to say here is, so that's how I calculate it, and that's my correlation coefficient. We're jumping around a little bit. I want to see how my sample, which could be small, how significant my sample is, because I'm trying to say something about loneliness and depression, for example, in general, and I have a little sample that I base my conclusions on. Now it might be that the sample that I get shows a very strong correlation, but how likely is it that there's no correlation, but I get a sample with very strong correlation? Of course, my sample is going to have some variation in it. And even if there's no correlation between the two factors, I might get a sample that shows some correlation. Some variation is understandable and is likely to occur. So when I get my sample and I measure the correlation by way of my correlation coefficient, I need to also check, is that correlation that I get from my sample, is that significant to conclude something about these two factors in general? So we can do a t-score again, and the observed t-score that I calculate from my sample by way of the correlation coefficient is given by this, with the degrees of freedom, the sample size minus 2, 1 for x and 1 for y. So just take note here that this is a division, and some places in the book has a typo where it doesn't show this division sign. Let's see if I can quickly find it. I know of one somewhere, and of course now on the spot I won't find it. No, I can't seem to find it right now. Quickly see if I can find it. Take a minute. I know there's a typo somewhere. There's a typo somewhere. On page 461, that one seems to be still good, as well as 460. And if you use those, then it's all good. If I look at the one in the very front of the book, it doesn't show that, so okay. So just be careful. Seems seems like most of those have it, but somewhere in some student's textbook I have seen that that's omitted. That's a clear typo. So just be aware of that. Okay, so if I look at this, my hypothesis test is going to be that there is no, let's say R of the population, let's say R population is 0, that there's no correlation. And then my research hypothesis is that there is a correlation. So I'm going to look at my t-test and decide whether or not to reject the null hypothesis. Whether the evidence from my sample is strong enough to suggest that there is a correlation. So I look at my loneliness versus depression example. I had a sample size of 6 and a sample correlation coefficient of 0.73. I calculate the observed t-score and I get a 2.15. And I can look at the love and conflict example where I had a sample of 7 people and I got an observed correlation coefficient of negative 0.64. The t-score corresponding to that is 1.88. So let's look at the first one, for example. I can calculate the observed t-scores coming from my observed correlation coefficient, and I want to see if that suggests that it's significant enough that there is going to be a correlation between them. Now, in general, I could have assumed a positive correlation from the start, and then I can change this to a one-tailed test. But if I have no idea, a two-tailed test is more common. So if I look at my t-distribution in this first example, degrees of freedom is 4 because it's n minus 2. Where is my cutoff for, let's say, an alpha of 5%? Two-tailed test would be 2.5%, 2.5%. What was the t-score that I'm looking for? Degrees of freedom 4. So let's go to my table. Where is my table? T-scores, t-distribution. Degrees of freedom 4 for a tail, 2.5%. Looking two-tailed, 5% alpha. Degrees of freedom 4, 2.776. 2.776. 2.776. Negative 2.776. And my observed t-score is 2.15. So sadly, that is not. So that is my t observed. And my conclusion would be that it is not significant enough, even though the sample has. This is why the test is so important. Even though the sample shows a strong correlation, it's not significant enough in terms of the variation that I suspect the population has, and all the factors combined, that I could have no correlation between those two factors and still have a reasonable chance of selecting, reasonable in terms of my cutoff, of selecting a sample of 6 people with this correlation coefficient. Now you could have, I'll just expand on this one and you can do this one for yourself. You could have looked at it first and said, well, loneliness and depression is a positive correlation, So we could change this to say I'm looking for a positive correlation, and then the null hypothesis is that there is no correlation. Then my two-tailed test will become a one-tailed test. And now, because I'm adding information, I know more information that I'm testing only positive correlation. What is my cutoff t-value now? Well, with a 4 degrees of freedom, I'm looking at a one-tailed, which is going to be 2.132, just out of curiosity. Which how does that put me? 2.13, oh, that's so close. That is so close. I'll exaggerate it a little bit, just for effect here. Cutoff, 2.132. So in that case, if I ignore the possibility that it could be a negative correlation as well, the evidence, and sort of knowing that I'm testing for a positive correlation, the sample is just significant enough to say that, yeah, if I'm under the null hypothesis, assuming that it's not a positive correlation, and now I get something like this, yeah, it's going to be just past my cutoff, so I can reject the null hypothesis. But if going into the study, I don't know what it's going to be, I can't look at my sample and say, I can't necessarily look at my sample and say, oh, the sample has a positive correlation, therefore it must be that the whole thing has a positive correlation. It might be risky to say. So a two-tailed test is a little safer, and I don't want to reject it for just any sample. I would have to have a much larger sample to really be more accurate. So with that smaller sample, there's a lot of variation that I can get, and a two-tailed test might be the safer way to go. You can do the love and conflict example on your own. Let's look at the sleep and mood example. Where am I holding this? I don't know. Sleep and mood example, where I'm now just emphasizing the steps a little bit more than our informal introduction to the hypothesis testing here. I have people like these in the study versus people for whom there's no correlation between the number of hours slept and the mood. So I'm going to do a two-tailed test here because I don't know which way it's going to be, and I can't necessarily conclude from my sample that it's going to be the same as what the sample suggests. Population 1 has a different correlation than population 2, or the same. In fact, then no correlation. So I have a t-distribution, 2 less than the sample size. So my cutoff t-score is like we've had before, 2.776 for a 5% alpha. I look at where my observed t-score sits, and it's at 3.23 in that situation. And then I can be much more confident in saying, yep, it's more extreme than my cutoff value. Either directions were covered. I'm going to reject the null hypothesis. There is a correlation between these two variables. And in fact, based on my sample then, there's a positive correlation between the two. So again, we'll have effect size. Now the correlation coefficient can serve as the effect size measure in this case. And depending if I'm two-tailed or one-tailed, that is going to play a role. So this first table now is backwards a little bit. In order for me to get an 80% power for the study, what is my sample size that I would need? So if I have an effect size of medium, small, or large, 0.1, 0.3, or 0.5, then this tells me if I have a very small effect size, very small correlation coming from my sample, I need big samples in order to ensure a good enough, high enough power. The other table, like we've seen many times before, two-tailed or one-tailed, depending on my sample size and my effect size, what is the power of the study. So we read those in the same way as before. To wrap it up, I'll just briefly mention that the correlation coefficient doesn't indicate causality. It doesn't indicate which variable depends on which one, which variable affects which one. For example, in this example, exciting activities as one variable, marital satisfaction as the other. It doesn't say. It might say there's a correlation between them. It doesn't say which one affects which one. Or it could be that some other variable affects both, and through this there is a correlation between these. It doesn't say anything about that. Lastly, the idea of an outlier. An outlier is something that doesn't really fit with the common values that I would get, sample values. Something a little more extreme. It's unlikely, but it can happen. It doesn't fit with the majority of the common values that I could get. Even though there's variety between them, some extreme values could occur in my sample. And that has an effect on the correlation coefficient, because it's, in this extreme little example, this one is going to mess up my z-scores a little bit. If I didn't have this one, I see a nice positive correlation, and my correlation coefficient will be fairly high. But because of this one, that's sort of indicating something that doesn't fit with the rest, it will have an effect on the correlation coefficient. And I have to keep in mind to not just blindly calculate the correlation coefficient and run with it, but look at if there are outliers, and there are fancier tests, more sophisticated tests to identify outliers, and perhaps get rid of them and then see what I have and see what the correlation is suggested to be by way of the sample that's a little bit more realistic. I don't want a couple of outliers to cause me to conclude that there is no correlation when in fact there could be. So it's important to be aware of the negative side effects that outliers and their presence might have.